Our speaker today is Hermie Monterde, and she's going to talk about quantum walks on graphs. Welcome, Hermie. The stage is yours.
Thank you. So everyone, for today, I'll be talking about quantum walks on graphs. This is just an overview, and I'm Hermie. My pronouns are she, her. I'm from the University of Manitoba, and today is May 5, not May 3. Okay. Okay, so first of all, I'd like to thank Sandra and the New York Combinatoric Seminar organizers for the invitation. I'd also like to thank Steve Kirkland and Sarah Plosker. They are my supervisors. Sarah Plosker in particular is the Canada Research Chair for Quantum Information Theory. Of course, I'd also like to thank the Department of Mathematics and the Faculty of Graduate Studies at the University of Manitoba for the financial support, which allowed me to be here. All right, so we'll just take it easy, all right? And so when we talk of quantum walks and graphs, the first thing that comes to our mind is like, okay, what is that, right? So let's just do a little bit of background. And here we're going to use graphs as mathematical models. And what do they represent? Well, so in physics, they have this thing called quantum spin network. And a quantum spin network really is just a network of interacting qubits. Now the qubits here, it might sound a bit technical, but when you say qubit, that just refers to a particle, and usually a subatomic particle. So it could be electrons, bosons, photons, etc. Now, in our case, we don't really care about that. We just call them all qubits. All right. So, okay. So now where does the graph come in here? So basically, this quantum spin network can be modeled by a graph where the vertices are the qubits, okay? And the interactions between qubits are the edges. That's where the graph comes in. And what do we want to do, right? Okay, so we have the quantum spin network, we have the graph representing it. What really happens is this. What we want to do is to assign a quantum state to a qubit, okay? So that's how we initialize it. And then what happens is that we want to determine the propagation of that quantum state. So basically, you put a quantum state in a vertex in a graph, then you let it propagate across the graph. So it moves, the quantum state moves across the graph. All right, and we want to analyze that behavior. And so to know how that quantum state propagates across the graph, we have the following, we need the following ideas. So first, I'm sure you're all familiar with the adjacency matrix of the graph. So basically, that's just a square matrix indexed by the vertices, right? So you have the UV entry is 1 if there's an edge between the vertices UV, otherwise it's 0, the entry. So it's just a 0, 1 matrix. And we define this matrix U of t, okay? So t here is a parameter. So t is any real number. And we define U of t as the exponential of ITA. I here is, of course, root of -1. And so you might be wondering, okay, that looks a little bit complicated, right? The exponential of IT times the matrix. But I'm sure some of you have seen that already, exponentiating a matrix. And so what's up with that matrix, right? But why do we define it that way? So it just didn't come out of nothing. It came out from Schrodinger's equation. And when you solve Schrodinger's equation, which is a differential equation, you get the solution to be this equation that we have down here. So P of t is just U of t EU. Now, this EU, okay, so let's break that down. When you assign a quantum state at vertex U, that is represented by the standard basis vector EU. To know how it propagates across the graph, you simply hit that EU by U of t, and you get P of t, which is the state of the quantum system represented by the graph at time t. So which means this answers our question. To determine how the quantum state propagates across the graph, we only need to look at u of t times eu. Now, if we take a look at this one, if t is 0, right? If t is 0, take note that this becomes the exponential of 0a, right? Which is basically just the identity matrix. It's the exponential of the 0 matrix, which is just the identity matrix. So this gives us t of 0 equals eu, which is the case, right? Because we started, okay, the initial state is eu. All right, so that's just the background of this. And so let's take a look at this transition matrix u of t. Right after this, I'm going to discuss a little bit about the types of quantum state transfer that is of interest to physicists and mathematicians. But our approach is pretty much graph theoretic and matrix theoretic. So this matrix is a complex symmetric unitary matrix, and this is called the transition matrix of G. And as we've seen from the previous slide, this is basically encodes all information about how the quantum states travel across the graph. All right, so it's a unitary matrix. So what about it being unitary? So if you recall, what is a unitary matrix? It has the property that the inner product of the youth column with itself is equal to 1, right? And the inner product of two distinct columns is 0. So if I take, for instance, the inner product of the youth column with itself, I get this, right? I use the complex inner product here. And this is interesting because if you really take a look at this one, okay, this happens for every column U. But since this matrix is symmetric, it happens for any row U as well. So it doesn't matter whether you look at rows or columns. So for this case, I believe we are using rows, right? So if you take a look at here, the sum of the modulus squared of these entries is 1 for each row. What does that mean? That means that every row determines a probability distribution, right? And so we can interpret then this quantity, okay? So you have the UV entry of the transition matrix U of T. If you take the modulus of that and square it, we can interpret that as the probability that the quantum state initially at vertex U is found in vertex V at time t. All right, just feel free to interrupt me if you have questions. I hope everything's clear for now. Okay, so let's go to this visualization because everything is theoretical at the moment. So let's try to see what's going on. So if we have the path on 3 vertices, right? And we assign a quantum state and an end vertex of a path, of this path. So this is the black vertex here. We assign that here, that's the time t equals 0. And then we look at what happens as we let t increase. That's what happens. But interestingly, okay, the quantum state assigned at one end vertex at time t equals 0 is now found, okay, at the other end vertex at time pi over square root of 2. Okay, and that is nice because that's what we call perfect state transfer. Now, before I bore you with all of these definitions, why is it important? Why are these things important to physicists and mathematicians alike? Well, so as you may already know, there's a lot of interest in building quantum computers, right? And I'm not sure yet if there's already an operational quantum computer that's available right now, but in order for that in order to construct that, it's important that we know when high probability quantum state transfer occurs. right? Because if we want accurate transmission between the qubits in the motherboard of a quantum computer, and that's exactly what's fueling this study, the study of perfect state transfer. So just to formalize the definition, we say that two vertices UNV exhibit perfect state transfer if the modulus of the UV entry of U of tau is 1 for some time tau. All right. Now, we have a relaxation of perfect state transfer. And this is silly. I'm sorry for the term. I did not create this, okay? But the relaxation is what we call pretty good state transfer. So as you can see here, for perfect state transfer, what we have is at a specific time t for which we attain 1, right, as the modulus of the UV entry. For pretty good state transfer, that's not necessarily the case. Rather, we have a sequence of times, okay, such that the limit of this expression is 1. So the main difference is that 1 in pretty good state transfer is the limit point of these quantities. Here, it is attained in perfect state transfer. All right. Later on, we'll see why these things are important. Okay, but we'll just take it slow. And as an example here, as we've seen, P3 has perfect state transfer between n vertices at pi over square root of 2, right, from our visualization. And P4, on the other hand, and we'll show that later, all right? But the path on 4 vertices has no perfect state transfer. Rather, it has pretty good state transfer between n vertices.
Can I ask a
Right.
question here?
Sorry?
I'd like to ask a question.
Go for it.
Is this sequence of times a totally arbitrary sequence? Does it have a limit? Does it have any properties?
Well, it is increasing.
An increase, just increase.
Yeah. Yeah.
So it may have a limit or it may go to infinity.
Yes. I think
Okay.
usually it goes to infinity.
Okay, thank you.
Yeah, yeah. Good question. Very good question. So we just basically take a look at it as there is a sequence of times such that as your time increases, you can pick those times for which the probabilities are almost close to 1. All right, all clear? So take note here, we are again interested in both of these quantum phenomena because we want that the quantum state at vertex U is transferred to vertex V, either with probability 1 or probability close to 1. Okay, and that represents the transfer of quantum information. And this is the mathematics behind that. All right, okay. So if you'd allow me, we can now move forward. All right, so first things first, right? The transition matrix U of t. What's the transition matrix again? It's the exponential of ITA, right? I mean, sure, we know the power series, right, of the exponential function. So the very first thing for sure that would come to one's mind, okay, in dealing with the U of t is to use the power series representation. But then you bump into an infinite sum, right? With I, with a matrix A, with the powers of a matrix. So that could be a bit painful. And that's not how we do things in the study of state transfer. Rather, we use matrix theoretic tools to deal with it. And yeah, here we use what we call spectral decomposition. So let's think of a real symmetric matrix A, okay? Because the adjacency matrix is a real symmetric matrix, right? But this applies to any real symmetric matrix. So if we have the distinct eigenvalues of the real symmetric matrix A, say lambda 1 to lambda r, and we denote the orthogonal projection matrix, okay, to the lambda j eigenspace as EJ, then this is a fact, okay, that you can write that real symmetric matrix as a linear combination of the orthogonal projection matrices where the coefficients are your distinct eigenvalues. So this is really just what's happening in here. Okay, so first things first, the EJs here have very nice properties. So first, how do we get the EJs? Okay, now you just need to believe me here that if given a J, a lambda J, take any orthonormal basis for a lambda J eigenspace, any orthonormal, okay? And then take the outer products and take the sum, you get the EJ. Thing is, the EJ is unique, okay? Each EJ is unique. However, it works even if you take any arbitrary orthonormal basis for the lambda J eigenspace. Now, this EJ, interestingly, is real because A is real, okay? The EJs are real, symmetric, idempotent, pairwise, multiplicatively orthogonal, okay? And they sum to identity. Very nice properties for a set of matrices. And lastly, this is the most important bit. If you take any analytic function of A will just yield the same spectral decomposition, except that the lambda J's will also be applied as the same analytic function. So if you take the exponential of ITA, you get the same EJs, except that the eigenvalues are now exponential of IT lambda J, which is nice, right? It's now simplified in a way, the form of the transition matrix U of T. So just an example for the path and 3 vertices. So we know this is the adjacency matrix for the path and 3 vertices. You can verify that the eigenvalues are 0 plus minus square root of 2, and the eigenvectors are this. Okay, so let's see, how do we get the spectral decomposition of A? Okay, the eigenvalues will serve as the coefficients, and that's what we have there, right? And these matrices are the outer products of the orthonormal basis for the eigenvectors. Now, we don't have a problem here because the eigenvectors are simple. There's only one, right? So we only need to normalize them and take the outer product. So for 0, you just need to normalize 1, 0, negative 1, take the outer product. You can verify you get this matrix. Okay, same for these 2 eigenvectors here. And then what happens now? If we take the exponential ITA, the EJs are the same, right? So this matrix is the same, this matrix is the same, this matrix is the same. What really happens is that you just exponentiate the eigenvalues. But since this is 0, exponential IT of 0 is just 1. That's why it's just a 1 here. Here, this would be the exponential of IT square root of 2 and the exponential of IT negative square root of 2. Moral of the story, if we take the 1, 3 entry, okay, if we take the 1, 3 entry of U of T, we get negative 1/2 plus 1/4 of this plus this. But take note here, if you add these 2 complex numbers, okay, the imaginary parts just cancel, and we get, this becomes just twice cosine T square root of 2, right? Simplifying, we get that. And then, ta-da! If we solve this to get 1, right, we get that the T should be an odd multiple of pi over square root of 2. So which means that there's always perfect state transfer at every odd multiple of pi over square root of 2. And we've seen that for pi over square root of 2 in the visualization. So this is exactly how you get, or how you know whether there's PST or not. The thing is, you don't want to do this for every graph, right? Right? It's such a hassle to compute all of these things. You want a characterization that would be a bit direct, right? So before we go to that, I'll give you another example, which you're probably quite familiar with, the complete graph and n vertices. All right. So as we know, the adjacency matrix of the complete graph is just the all ones matrix minus the identity, right? Now, I'm using matrix theory here because that's my jam. So the all ones matrix, the eigenvalues of that are just n and 0, right? N with eigenvector, the all ones vector, and 0 with eigenvectors E1 minus EJs. Okay. Since the adjacency matrix here is just a translate of the identity, we get that the eigenvalues of A is just n minus 1 and negative 1, which we already know, right? For the complete graph. So, okay, don't fret here. Okay, we don't necessarily need this, but I'm just putting it here to highlight the importance of knowing the properties of the orthogonal projection matrices. So how do we get the spectral decomposition? We get n minus 1 times the normalizing 1, right? And taking the outer product. So we get this one. Similarly here, plus negative 1, sum of all of these outer products. Now, you don't need to know that because this is just what we need to know. What's the outer product of 1, the all ones vector with itself? Isn't that just the all ones matrix, right? So in this case, we just get n minus 1 times 1 over n times j plus negative 1 times the orthogonal projection matrix is sum to the identity. But we already have this as an orthogonal projection matrix here. So the other orthogonal projection matrix should be the identity minus that. And that's exactly how we solve that there. In the complete graph, unfortunately, it's boring, but I'm going to have to get back to this example later on. And if you look closely, the spectral decomposition here yields the transition matrix. And if you check the entries, okay, we see here that, okay, if U and V are distinct, okay, if U and V are distinct, then the modulus of the UV entry of U of T is bounded above by 2 over n. Okay, moral of the story, the complete graph has very low probability, right, to travel from vertex to from a vertex to a distinct vertex. It's very low probability that you can find it in the other vertex, the quantum state you started with. But as you can see here, the probability from vertex U to itself, right, is bounded below by 1 minus 2 over n. What does that mean? This means this. Okay, the modulus of the UU entry of U of T, this is the square of that would be the probability, okay, that you put a quantum state at vertex U, and you can still find it there at the later time. Now, since we've seen here that that's bounded above by a big number, right, 1 minus 2 over n, that's a bit of a big probability. That means that the quantum state at vertex U tends to be there, tends to stay there for any time t in the complete graph. Okay, we'll dig that a little bit later. Let me just talk to you about any questions so far. All good? Okay. I'm going to bring out some combinatorics after some graph theory after I discuss a little bit of concepts here. So strong co-spectrality. So what is this? And there's been a bit of work in this topic recently. If we have perfect state transfer between two vertices, that's just equivalent to this occurring, right, at some time t. All right. What does this mean, everyone, from a physical point of view, right? Okay, before we do the physical point of view, this basically just means that the UV entry of the transition matrix at time tau here is a unit complex number, right? That's just what it means here. And ultimately, this means that the quantum state at vertex U at time tau, that is sent to vertex V via this complex, with a complex phase. And that this gamma is actually the entry here. Now, applying spectral decomposition of U of T given A here, we get this equation right? But we just hit it with an EU. All right, so what now? We have that. We now use the fact that the EJs are pairwise multiplicatively orthogonal, right? So if I have this equation equals gamma EV, if I hit both sides by EK to the left, okay, everything here cancels, right? Because the EJs are pairwise multiplicatively orthogonal. Everything cancels except for the single entry corresponding to EK. So you get that, right? And here you just get gamma EK EV. And this happens for every K. And since the EKs are real, right? When does this happen? If these vectors are real and they just differ by a constant here, this means that these vectors should just either be plus or minus multiples of each other, right? For each K. Now, it's a bit hard to imagine this, right? But let's put a name into it. So we say that U and V are strongly cospectral if for each orthogonal projection matrix J, it's either the projection towards U and V are equal or opposite signs. Okay, now that's a little bit hard to imagine for if you're not very comfortable with matrices. So we give this equivalent definition that if you take, so for strong cospectrality, if you take an orthonormal basis, W1 to WK for every lambda J, okay, for the lambda J eigenspace, you get this. In each vector here, it's either the uth entry equals the vth entry for all L for each there, or the uth entry equals the negative of the vth entry for each of them there. That is, if you think about it, like that's a little bit unlikely to happen, right? And so nonetheless, we'll see the importance of this later on. So in this case, if U and V are strongly cospectral, so again, these J's are tied in to every eigenvalue, right? So we can define these two sets. The eigenvalues for which these projections are equal and the eigenvalues for which these projections are negative. And we denote them by sigma UV plus and sigma UV minus. All right. Okay, so any questions so far, everyone? I'll do this characterization of PST, and then the characterization of PGST will then just follow similarly. And then after that, we'll take a look at graphs that have been that have caught the attention of physicists and mathematicians, because those graphs are attractive to physicists when it comes to building or some modeling the quantum spin networks that we talked about at the very beginning. Okay, so this is, we've seen a while ago that the existence of PST is equivalent to this equation being satisfied, right? Quantum state at vertex U is mapped to vertex V at time t for some complex phase gamma. Okay. All right, now this looks a little bit overwhelming, but let's go back a little bit to the previous slide here. This is the PST condition, right? And it requires that this holds for every K, right? So which means that the eigenvalues here in the spectral decomposition, we can classify them into these two sets. So really what's happening here is that these eigenvalues, right, is either equal to gamma or they're equal to negative gamma, assuming strong cospectrality. So that's really just what's happening there. So, okay, just think of this as the exponential of IT, lambda j's from the lambda j sits in here is gamma, or it's negative gamma if it sits in here. This gamma turns out to be unimportant because this is really what happens here. If I pick an eigenvalue sitting in here, if I fix an eigenvalue, then gamma is just exponential IT lambda 1, right? So what happens here is that if I divide both sides by gamma, I get this. But here, if I divide by gamma, I get this, with lambda 1 being fixed. Okay, so now we have this nice equations, exponential of the differences being 1 in this set and -1 in this set. So what now? So we want both of this to hold at the same time. Okay, equivalently, there is some time t for which, when is the exponential of this equal to 1? Isn't that just time? The t times this difference is an integer multiple of 2 pi, right? Or here, it's an odd multiple of pi, right? And then if you take a look closely, what happens here if you divide? So if you divide this quantity with this quantity, right? Because this is basically just any integer multiple of 2 pi. This is any odd multiple of pi. When you divide them, right, the t cancels, but you just get lambda 1 minus lambda k over lambda 1 minus lambda j. It turns out to be rational, right? Because the pi's just cancel. And this is now where it gets interesting, because perfect state transfer necessitates that the eigenvalues satisfy this rather odd number theoretic condition on the eigenvalues, right? This is the first time that they've seen this kind of condition, and all of the strong co-spectrality combined with that actually gives you a characterization of perfect state transfer. So two vertices exhibit perfect state transfer if and only if they are strongly co-spectral, okay? And the eigenvalues in this union, okay? And this is actually stemming out from this. And that this also implies that perfect state transfer is rare, because all the eigenvalues in this union should be of this form. It should be either all integers or quadratic integers, okay, in some field q squared of delta. And there are in a way that's a bit rare, right? Because if you think about the adjacency matrix, it's a 0-1 matrix. So the characteristic polynomial tends to be irreducible, right? But here, what we're saying is that we want the eigenvalues to be either all integers or roots of quadratic polynomials. And that's why perfect state transfer is rare indeed, as proven by Chris Godsell in 2012. So that's the moral of the story. It's rare, right? And that's why PGST has been studied. And we asked this question, if this is not possible for some time t, how about a sequence of times tau sub k, such that 1 is the limit point? That's really what we want to see here. Any questions? All right, now I'm going to skip this PGST because it's really just the same. However, I would like to highlight this characterization of PGST, where it also requires strong co-spectrality between vertices, but this is the mathy and very interesting part, okay? It also requires the second condition. And what is the second condition? It's basically just a condition in the linear dependence of the eigenvalues. So take a look closely here. So we have here eigenvalues sitting in this set and eigenvalues sitting in this set. We want LJs and MKs to be integers, okay, such that if this equals 0, this linear combination equals 0, and the sum of the coefficients is 0, then the sum of the MKs here should be even. All right. Now, of course, let's address some questions that you may have in mind. You may be thinking, so when is PST and PGST equivalent? Because PGST is a relaxation, right? So both of these are equivalent if and only if the eigenvalues here satisfy this condition, the number theoretic condition we mentioned a while ago. Outside of that, PGST is on its own, okay? And then, okay. What if the second question, of course, that you may have in mind is what if the eigenvalues are linearly independent, right? So let's think for a bit. Think of the adjacency matrix. Take a look at the trace, right? The adjacency matrix has 0 diagonal entries, right? So the sum of the eigenvalues of the adjacency matrix is 0, right? So which means that the eigenvalues are linearly dependent for all of them for the adjacency matrix. However, we are just looking at these two sets and the union, okay? We're talking about this union. This union is not necessarily all of the eigenvalues. So which means that that union could be linearly independent. And so it can happen indeed that this sum cannot equal 0. And that's why we have this thing about paths. Okay, so in this, we're just using this characterization where if you have two strongly co-spectral vertices and the eigenvalues, sorry, this should be the union of this and that. If the eigenvalues there are linearly independent, then you get pretty good state transfer between U and B. And that's exactly what led physicists and mathematicians to classify PST and PGST in paths. Okay, first here, unfortunately for paths, P2 and P3 are the only ones that exhibit perfect state transfer. And that's right, so it's very rare. So like people are like, okay, fine, let's study the PGST instead. It turns out that for paths, there are infinitely many that exhibit pretty good state transfer. Okay? So for a very specific example, the path on 4 vertices, you can verify that these are the eigenvalues, okay? And if you get any two mirror symmetric vertices in path, so that may be the end vertices or the internal vertices, it turns out that the union of this is, okay, it turns out that this is actually a linearly independent set over Q. Okay, and since that's a linearly independent set over Q, just applying this theorem, we get that PGST occurs between vertices 1 and 4. Okay, before I move on to this will be my last. Okay, I'm almost done. So paths are interesting to physicists and mathematicians because they are the sparsest graphs that are connected, right? So in terms of the problems here in quantum state transfer is pretty much rooted in the problems related to the application. Because if you want to create a quantum computer, you want the minimum number of qubits involved, right? But they're connected because you want to get from one end of a quantum computer to the other end. So you want to transfer that information reliably, but at the same time with the least resources possible. And that's why they are really looking at paths. Okay, any questions? All right. Now, this will just be quick. This is what we call sedentariness. And this is my current research, not the PST or PGST, but we'll see how this will tie into PST and PGST. So a vertex is sedentary if for some constant, positive constant C less than 1, the UU entry modulus, okay, is at least 1 minus C. So take note that 1 minus C here is positive, right? So what we're looking at here really is that the quantum state at vertex U, okay, tends to stay at vertex U because this probability is always positive. So the quantum state tends to stay at vertex U for any time t. This is what sedentariness is about. And we know that since this is just the sum of all probabilities starting at vertex U. So this is from U to U, U to V, and U to J, where J is not equal to UV, right? And the modulo squared of that is 1, as we know from the very beginning. So moral of the story here, if this is always positive, right? Actually, it's not always positive. Sorry, that's an incorrect term. Rather, what we're saying, this is bounded away from 0. That's really what we're saying. So if this is bounded away from 0, this can never be close to 1. Right? And this is never close to 1, then a sedentary vertex cannot exhibit PGST. And those that exhibit PGST cannot be sedentary. So in a way, sedentariness, by studying it, we also know which graphs avoid high fidelity quantum state transfer. So just an example which we've given before, any vertex of the complete graph, an n vertices, is sedentary because of this bound that we've seen at the very beginning of the talk. And we'll just study, I'm currently studying twin vertices. And twins, as you may already know, these are just vertices with the same neighbors. And we define a set of twins to be a set where every pair of vertices are twins. All right. And we have this lemma, which says that two vertices are in a set of twins if and only if this difference of standard basis vectors is an eigenvector corresponding to 0. And this is really my main result in one of my research works. We can skip this or we can go back to this later on, but this is just basically what's happening. If you have a set of twins T, okay, if the size of that is at least 3, then each vertex there is sedentary. And that explains the complete graph. Sorry for the, there's a truck outside. Okay, so think of the complete graph. So the complete graph on 3 vertices, all vertices are pairwise twins. They're adjacent to, right? So Kn, every vertex there is a set of twins. So the complete graph on at least 3 vertices satisfies the first condition here. So they're always sedentary. I also have a characterization for sedentariness for twins of size at least 2. And basically this F here, okay, if I may just explain that. So if T is your set of twins in the graph, right? There could be 2 of them, 3 of them, 4 of them. You don't know, as long as you know this M is at least 2. If you index the first M rows of the adjacency matrix by the elements in T, right? You get that EU minus EV is an eigenvector for A by this previous lemma here, right? So that's an eigenvector for the eigenvalue either 0 or -1. The thing is this, so since we already know these are eigenvectors, if I take an orthonormal basis of eigenvectors corresponding to either 0 or -1, these vectors can be orthonormalized, right? But you could also have other vectors, eigenvectors corresponding to 0. And that's exactly the F that I'm talking about here. So this matrix really just comes from orthonormalizing this. And you know, when you extend this to include the vectors in U, you get this other matrix F. And that's what we have there. So what we're saying here is that we only have 2 twins, but the UU entry of that matrix F is positive. Then each U is sedentary. And just some open questions in case you're interested in quantum walks. So these are just, I think these questions are pretty much being worked on currently by a lot of people in the field and even the physicists. And we asked the following questions. What are the sparsest families of connected graphs that exhibit PST? So for instance, the hypercubes are really famous. The hypercubes exhibit PST for any hypercube. And the hypercubes, the physicists love them because they're very sparse. Now the question is, can we find more sparse graphs than the hypercubes? That question is not answered yet until now. And of course, we like sparse graphs. So we also ask the question, is there a characterization of PST, PGST, or sedentariness in planar graphs? Because, you know, in planar graphs, right, you can't have too many edges. Otherwise, they would contradict planarity, right? Also in Cayley graphs are a little bit difficult, honestly. So not a lot has been, there's a lot of study there, but there's still a lot of work that needs to be done there as well. Characterization of sedentariness and distance regular graphs. We can also ask, we already know that the path and n vertices exhibits PGST for infinitely many n, but not all n. So we ask, for those n that are not in that characterization, do the vertices PNs, are they sedentary when they do not exhibit PGST? That's also not known. And finally, this interesting question where addition of loops. So in state transfer, when you add a loop on a vertex, that means you're adding a magnetic field on the qubit corresponding to that vertex. But again, we're not physicists, so we'll just leave that to them. But addition of a loop on a vertex is basically just adding a weight on the diagonal entry of the adjacency matrix, which kind of messes up the spectral decomposition and all that. Nonetheless, it's a valid question. If we add a loop to a vertex of a graph, will that induce sedentariness, or will that induce PST or PGST? That's also another long-standing question. And that's all. Thank you, everyone, for listening.
Thank you very much, Hermie. Let's thank the speaker. And we'll take questions now.